Hello. Today we will talk more about the basic statistics. In part one, I gave you some basic intuition behind t-test, what exactly is done to give you p-values. Today we will continue this, how to extend it to different tests. Okay, so I mentioned that in many parametric statistics, it's very important to check what is your distribution of data you are trying to investigate. And it is because although most of parametric statistical tests are designed for to work on normal distribution. And it is because this normal distribution is very popular, very often occurs in nature. And here I will give you intuition why this distribution is so popular, why nature is so often displaying this normal distribution. It was shown with central limit theory that data which are influenced by many small and unrelated random effects are approximately normally distributed. So what it means is that if we have these variables x, x2, xn, and each of those is coming from different sources, unrelated sources, and whatever is distributions of data in x1 or x2, if we look at the average, the distribution of averages, it will be approximately normal Gaussian. And here it is why. So you remember that in previous lecture we calculated distribution of means. And this idea is very similar. So if we have, for example, normal distributions like here, and we will take a random number. If we take, let's say just two samples from these distributions and calculate mean, and we will repeat this process 1000 times. So distribution of means from those two samples, it will be something like that. It will be Gaussians, but with smaller width. If we, for example, will take a sample from, if we will take not two, but 30 samples, calculated mean from these 30 samples, and repeat this process over and over again, then distribution of means, it will have also this Gaussian shape, but now with much narrower width. And it is how we were talking about distributions of means. And it is because it is very unlikely by chance to take 30 samples that the mean of these 30 samples would be, let's say, here, because all those samples would have to be somewhere around this edge. It is much more likely to have distribution mean of those 30 samples somewhere around the middle, because if we take some samples from this side, some from this side, and so on, then on average it will be close to the average of the original distribution. And what is amazing is that whatever is the original distribution, the end distribution of means, will tend to be a normal Gaussian. So for example, if we have this uniform distribution, and again we would take, let's say, two different samples and look what is the mean, and repeat this calculation over and over again, then what we will find is that the distributions of means will have this triangular shape. But if instead of 2, we would take again 30 samples from this and repeat this process, that we will take 30 random numbers from this distribution and calculate mean, and again take another 30 random samples and calculate mean, what we will get is it will be this normal distribution. And similar with exponential distribution, that if we take only two samples and calculate mean, it will have this somehow shape in between normal and original distribution. But if we will have not two, but 5 or 30 samples, it will get more and more Gaussian-like. And even if the distribution is parabolic, if you do the calculations that if you take some 30 random samples from this distribution, the mean will be somewhere around 0, and it will be less likely to get this extreme values. So if we have this 30 randomly chosen samples and repeat this process over and over, we will end up again with Gaussian distribution. It even works if we change this process a little bit. Let's say that one variable is taken from this distribution, other variable from this triangular distribution, other from rectangular, some variables from this discontinuous distribution, and so on. So if we take some random number from this distribution, other number from this, and so on, and we will look what is the average, and we will repeat this process over and over again, then distribution of those averages again will be normal. So what does it mean, how it relates to natural phenomenon? Well, many things are governed by many different factors. For example, let's talk about height. So height of people, let's say at age 30, it will be approximately has this normal distribution. And it is because height is not governed by one variable, but many variables which can be treated as this unrelated variable. So for example, what was the genes from mother, what was the genes from father will affect height. It will affect what type of diet people have, what type of, let's say, fatty food or omega-5 they add. All those different contributions, all those things are unrelated, and it will differently contribute to height. And even environmental factors like is this person working physically, carrying some heavy objects? If it does, then it will compress tissue, and it will cause that those people will be slightly shorter. So environmental factors, what we eat, and genetic factors, all those things can be treated as independent variables, and our height is results of interactions between all those variables. So it is a similar case as here, that genes are taken from some distribution. Our food can be also treated as a variable from a completely different distribution. And if we look at the combined effect of all those variables, then on average it will be normal. You can think about also, for example, about leaves. If you measure the length of leaves, it also will have this normal distribution. So let's assume that the length of the leaf depends on the amount of sun, and also maybe on which branch this leaf is growing. If it is smaller branch, then maybe leaves can be smaller. On bigger branches, leaves will be bigger, and so on. So you can assume that maybe there is some leaf on small branch, which is kind of limiting the size of this leaf, but it will have a lot of sun, so it will somehow compensate for this smaller branch, and it will make this leaf a little bit bigger. So the sun and branch width are two independent variables, and they will interact, and because they are they can be treated as a random, the resulting distribution of leaves will be this normal distribution. And in this example of leaves, again there will be not only those two factors, but many other factors will be contributing to it, making it more Gaussian-like. So the test we were talking about, assuming these Gaussian distributions, are really good in many cases. And even if data is not exactly Gaussian-like, often those tests will give us a good approximation of statistical significance. Okay, but what happened? So there's many ways to test if your data is distributed in Gaussian way. The simplest is just looking at your data. So plotting your data in form of histograms, for example, it can give you right away good idea if it is Gaussian or not. If you have, let's say, thousands of distributions and you cannot look at all of them, you can, for example, apply some tests like looking at the skewness or kurtosis, or even you can apply some non-parametric tests of like Kolmogorov-Smirnov test to check normality. But I will not talk about it in more details. But if it happens that your data is not normally distributed, for example, it is skewed in one direction, there are some simple ways that sometimes it can be this problem solved. For example, let's say that we have here this sample made up data that we have here 8 students, 4 of them majoring in history, 4 of them majoring in English, and we ask them how many classical music CDs you listened last week. And in history major, 1 student listened to 4, other to 16, and 2 other to 9. For English major, it was 1 36, other 9, 0, and 9. So if you plot distribution from those 4 numbers for history majors, it looks more or less like Gaussian, but for English, it is a quite skewed distribution. But if we apply, for example, square root to those numbers, then it will make all those big numbers to be compressed much more than small numbers, so it will reduce this skewness. So in this example, what we have, if we apply to this raw data this square root, we will get now this data compressed, and similarly for English majors, now it will look more Gaussian. And now you have 2 distributions which are very similar to normal distributions, and now you can apply t-test. And there is some discussion in statistics circles if doing such transformation is valid or not, but majority of statisticians think that it is a valid method to apply the transformations. The one important point is that you cannot apply transformations only to one group. You have to apply exactly the same transformation to both groups. So history majors and English majors data are both transformed by the square root. So as we said, if we have this data skewed, we can apply this square root transformation. So if data is before, then after it will look like that. Another transformation, it is inverse transformations to 1 over x. So if you have data like that, if you each of those data point take inverse, so make, for example, from 10 to be 1/10, then you will end up with this much more normal distribution. So again, for some data, it will be better to apply the square root transformations to get more normal distributions. For other data, it may be more appropriate to apply this 1 over x. And you can think about, you can find also informations about many different transforms which could be helpful. Okay, so this is that about transformations, and you have to keep in mind that it is not always clear what is the best measure of our variables. So we think that measuring something in this units 1, 2, 3 is the best way. So transformation of this by square root can be somehow views as some unnecessary things which may add distortion. But for example, if we think in what happens with our auditory perception, it is working in a logarithmic system. So we hear something what is twice louder, what in fact it is logarithmically louder if you look at the power of sound. So if we look, for example, perception, then working in this linear scale of power of sound, it may be not appropriate, and taking the log transform of this could be much better. So similarly with any other things, it's not always obvious that this type of linear scale what we are used to work with is the best way to quantify things. So doing transformation, maybe for this system, this transformation is more meaningful than just a linear scale. Okay, so this test what we were talking before are called parametric tests because they rely on parametrizing this Gaussian distribution by mean and standard deviation. So knowing those two numbers about distribution, it allows us to run those statistics. But sometimes data are not normally distributed, and it's very difficult to somehow transform them in a normal distribution. So there are also tests which are called non-parametric tests. So here they are not assuming, there is no need to assume or to check what is the distribution of data. And one of such tests is, for example, Wilcoxon-rank sum test. So here let's explain it on example. Here we have some fictional data, again for 8 students. So let's say that we ask students how many books you read recently, and based on some psychological tests, we divide students in highly sensitive and not highly sensitive. And for a group of not highly sensitive students, we found that one student read 0 books, one read 3, other 10, and one 22. For sensitive students, we found that one read 70, 30, other 36, and so on. And now, instead of looking at distribution of those numbers, what we can do is just rank those numbers. So, for example, if we put together those values, we will find that 0 is the smallest, 3 is the second smallest, 10 is the third. But now the 17 is the fourth smaller number, so we will assign to 17 rank number 4 as a rank 4, 22 it will be rank 5, and so on. So now, instead of these original numbers, we will work with those ranks. And these tests develop that they can say if this is significant difference in ranks. So you could intuitively imagine that if in both groups there would be some similar distributions of books read, then if you sum up ranks for this group and for those group, then you should end up with more or less a similar number. But if there is some significant difference between those groups, then sum of ranks for one group, it should be significantly different than for other group. And this is what is this test using, that it's discarding original scores and is transforming to ranks. So keep in mind that, for example, if one of those numbers would be extremely high, for example, if the students would be reading not 75 but 175 books, it still wouldn't affect this test. That if this is ranked 8, so whatever number it would be higher than 45, it would have exactly the same effect. So the absolute values of those numbers are less important. just only what is the relative rank of those numbers in relations to each other. And in biology, where data are sometimes not normal distributed, is useful to apply such non-parametric tests as this rank order test. The other things are more recent development. So all those tests which I presented so far were developed quite long ago, and those are based on they have some analytical solutions, but with advances of computers and this computational powers, we can apply some new type of tests. And those are computationally intensive methods, and they are called as randomization tests, or shuffling tests, or bootstrap tests. And they can be alternative as to parametric and non-parametric tests, and they are widely applicable, and they are not so often used by researchers. Still, if you look at publications, mostly people are using standard parametric tests like t-tests, but with more complex data, like for example with analyzing some neuronal data, this shuffling test, randomization tests are really important tool to test for significance. So how those tests look like? So here is a slide from a previous part of our talk. So if we have this normal distribution, what I was giving intuition behind t-test is that if we want to see if this is a distribution of general populations, and we have some comparison population, let's say 64 students which have on average score 220, we want to know if it is significantly different from general population. So the way how I was explaining how it can be done is that we can, from this population, take random sample of 64 students as this population, calculate what is the average of this, and plot it here distribution of those averages. So we can take another group of 64, calculate average, another group of 64, calculate average, and now we can compare how this group of 64 students, how it compares to this distributions of means of 64 students from original distribution. And if it is on the edges in less than 5% of tail of this distribution, then it would be significant. And what I said about t-test is that we don't need to do this sampling, that there are some analytical formulas that based on if we know what is the mean and standard deviation of this distribution, we can right away calculate what would be these distributions of means for this 64 randomly sampled students. But the idea is that you will do this sampling is the same for any distributions. That, let's say here we have some completely different distributions, some bimodal distribution, and we want to compare if this distribution of this 64 students is different, then we wouldn't have some right away analytical formula, but thanks to computers, we could sample this, let's say, bimodal distribution many times, generate this distribution of means, and now we can see how likely it is by just random drawing from original distribution to get a mean which is the same as for compared distribution. So this what in t-test I was saying that we can do by drawing, but in fact we are doing just from analytical formula. With computers we can do such drawing from any arbitrary distribution and compare it to distributions we are investigating. So the idea is very similar. So let me do some example. So here is the same data with highly sensitive and non-sensitive students, how many books they read. And here we can calculate what is the average of those books which sensitive students, non-sensitive students read, and this highly sensitive students read. So you see that mean is 8.75 for non-highly sensitive, 43 for this highly sensitive. And as you remember, this distribution is not normal, it is highly skewed distribution, so we couldn't apply just simple t-test on this. The way how to do this shuffling test, this randomization test, is the following, that we can put all those numbers in one row. So here we'll take the 0, 3, 10, and 22 books, and later the 70, and so on. And now we can assign groups. So originally, those first numbers are belonging to group 1. This second 4 numbers belongs to group 2. And we can calculate what is the mean for the first and for second group, and it is what we did here. But next we can make some random assignments of those groups. So now we can see what would be expected difference between those means if we would have just this random assignments of groups. So now let's say that by chance first person is assigned to group 1, but the fourth person is assigned to group 2, and so on. In another, and again, we will calculate here what is the average for people who are assigned at group 2, what is the average for people assigned to group 1, and we will calculate what is the difference between those groups. And again, we can do it for another permutation of those groups, and so on. And in this simple example, I think there is 70 different combinations in which you can assign those groups. And we can calculate what is the difference between average for one group and other randomly assigned group, and see how it compares to original difference. So here are some another examples. So this random assignments is, for example, here that if it is actual data, here in this new generated data, this person from this position was replaced here, and we calculate what was the difference. We will calculate what difference was for some another random assignment, and so on. So from each of those random assignments, we will calculate, as we said, means for each group. We will calculate what is the difference, and now we will plot, look what is the distributions of those differences. So here is all the possible differences between those different random assignments of groups, and we can sort them from the smallest to the highest. And what we can see is that this original difference of 34.5 is second highest difference. So it is above of this, if in this distribution, it is above of this top 5%. So we can say that this is a significant difference between those groups. So again, here with this shuffling method, we didn't have to assume anything about distributions of this data. Basically, what we try is that by randomly reassigning those groups, what would be the expected difference between those groups. And what we found is that it is very unlikely that with any assignment, only with one other assignment, we could get bigger difference between groups. So it is in top 5%. So we can say that this is a significant difference. So the null hypothesis, it was that there was no difference, and here by that we will reject this null hypothesis. Okay, so and this randomization test, as I mentioned, is getting more and more popular. For example, with my data, where I do a lot of analysis of spiking data, so I'm looking at times of spikes, at patterns of those spikes. So it is very difficult for me to somehow apply standard parametric tests. Rather, when I see some patterns of spiking activity, and the question is this pattern possible to occur by chance? What I have to do is I have to shuffle spike times of my data many times, hundreds of thousands of times, and see how likely just by chance I can get this pattern which I was interested in. So if it is unlikely to get by chance this pattern, it means that this pattern is really something likely to be meaningful. So for example, I apply this idea to test if there are some specific spiking patterns occurring before seizures. So to see if those patterns are just randomly occurring, or they are really occurring more often than expected by chance before seizures, I apply this shuffling test to evaluate its significance. Okay, the other topic which I wanted to cover, which is often used in neuroscience, is correlations. So here we have this example of correlations of two variables. So let's say that here we are measuring what is the satisfaction from marriage, and here how many exciting activities partners are doing. So as you can see, more exciting activities partners are doing together, then there is higher satisfactions from marriage. How correlation coefficient is calculated? I like this definition, which is that you convert to z-scores values in first variable, and independently you convert to z-scores in second variable, and now you are just multiplying values in first variable by second and just summing it up and dividing by number of samples. And if correlation is the maximum value of correlation coefficient is 1, so it is perfectly correlated. 0, it means no correlations, and -1, negative correlation. And in MATLAB, you can apply this CORE-COEF function, which will calculate correlation coefficient. So it can give you what is the value of correlation coefficient and also what is the significance. So in going to this example, to calculate this correlation coefficients, the one way to do it is to convert those numbers to z-scores. So probably somewhere here it would be mean, so it would be 0, here it would be positive, here negative values. And similarly, we would convert those values of marital satisfaction to z-scores, so that here it would be around 0 and it will be positive and negative values. And next we will multiply z-score of this point by z-score of the same point on this axis, and we will just sum it up and divide by number of points, and it will give us a correlation coefficient. And here, because this data is correlated, the correlation coefficient probably will be positive. Okay, so what are the things to keep in mind when calculating correlation coefficient? So it is very intuitive measure, but it is only measure of correlation. And maybe before talking about it, I wanted to also mention that when you calculate, when we get the correlation significance of correlation, how significant is correlation, it is similar to calculating t-test. So there is this nice connection I wanted to tell you, which basically say that even that here we are calculating correlation coefficients and not t-test, mathematically those things can be equivalent. And here it is how. So imagine that you have two populations and you have some scores for one population, for other. And now you can just look what is if there is any correlation between x and y values on x and y axis. So if you see here that probably here is some significant correlation, it is equivalent to doing t-test between those two groups. So you have distributions of one group, here distributions of points in second group, and you can calculate what is the t-test, what is the significance of that those distributions are different, and it will be the same as significance of correlation coefficient. So here are another examples that if you see here the data from those two groups highly overlap, then even that the correlation coefficient seems to be positive, the p-value probably will not be significant from this correlation, and it will be the same as you would calculate if there is significant difference between those two groups using t-test. And I will not go into math, but I just wanted to mention that t-test and calculating significance value with correlation coefficients, those are not two different beasts. Mathematically, they are tightly related. So what I started talking before is that correlation does not imply always causality. So in this example, what we had that higher satisfactions from marriage was correlated with more activities done by couple together. We don't know what is the cause and what is the effect. That, for example, it as well could be that doing more exciting activities is improving satisfactions from marriage. Or it could be that marriages which are already more happy, they are tending to do more exciting activities. Or it could be something else. There could be some other factors, like for example work pressure, which is affecting both things. So let's say that if both people have less work pressure, then they have more time for exciting activities and for and it causes also more satisfaction in marriage. So it does not have to be that exciting activities are directly affecting marriage, but rather some other variable. And from correlation coefficient, we will not get answer which of those things is true. To do it, we would need to have some additional studies. So one way how to deal with that, I would imagine that maybe you would have to have some group of people look over time. That let's say you will have people with some similar satisfaction in marriage, and one group of people you would ask to do more exciting activities, other people you would ask to do normal or low level of exciting activities, and now you can compare after some time both groups. So if the exciting activities were improving this marital satisfactions, you should see it in one group and another, and not in other. But if it was some other factor, then it may not affect this satisfactions from marriage. So what I'm trying to say is that just looking at these two numbers, satisfactions from marriage and exciting activities, will not tell us what is causing what. It has to be some additional changes to experimental design to tease out what is causing what. One other things to keep in mind when working with correlation is that sometimes things can be correlated, but we may not detect it. So for example, here is some functional data with school grade level and knowledge of geography. So students who are older have higher knowledge of geography. But if we would only analyze data from the first 3 grades, because there is so big spread of values, we may not detect any significant correlation. So if we only take data from first 3 grades, we may find some very small correlations, but it may not be significant. So by looking only at part of the data may not reveal a full relation between variables. Another thing about correlation coefficient is that it is highly affected by outliers. So for example, in this data, just by eye, it seems like there is this positive correlation with, in this case, with happy mood and how many hours people slept last night. But because this one point is so much far, if we calculate correlation coefficient, we will find that correlation coefficient for this data set is minus 0.18. So it will be negative correlation. So what to do with that? Well, it is, as before, important to visually inspect your data. Your eyes are the best way to detect some outliers, and it is completely okay to exclude some data points which are outliers. So if you are writing a paper about this data, you can say that we had this 1, 2, 3, 4, 5, 6, 7 subjects, but data from one subject were excluded because he slept less than 1 hour, and we only included data for people who slept between 4 and 12 hours. So it seems like this person who slept so little, it's quite unusual. So it is, if you explain it in method section what you did, it's okay to exclude some data points if it is justifiable. The other things which may affect correlation coefficient is unreliability of measurement. So let's say that there is perfect correlations between two variables, but if we don't have some enough precise measurements, if let's say we have noisy voltage meter to calculate some, to quantify some voltage changes, we will get some variability, and more variability, it will reduce correlation coefficient. So in our data, if data is more noisy, we will get lower correlation coefficient, and it is not because those variables are less correlated, it is because we were not able to enough precisely measure it. Another interesting things about correlation coefficient is that again, it is important to visually examine data. So here I showed some example where we can have some fictional data where I'm plotting here what was the score from some test, and here it was time, how much students preparing for this test. And let's say that this is data from one class and this is data from other class. So what we can see is that this class seems to be harder, easier. This class is easier. So here you can see that students can get better scores with less time spent preparing for this test. But within this group, you see that students who study more, they got this better grades as expected. And similarly for in this class, students who were studying more got better grades. But because this class was so more difficult than this one, if we calculate what is the correlation coefficient between time spent preparing and score, we will get negative correlation coefficient values. So again, it would be probably misleading to analyze those two groups of data together. Probably better it would be analyze first analyze data from each class independently, and then to say to look if for all the classes with correlations between time and scores are similar. So again, for the first, when thinking about it, it may make sense to combine data from all classes together to calculate such, to look if there is some correlation. But as in this case shown, sometimes it can be misleading. So again, examining by eye data, raw data is very good idea before doing analysis. Also, correlation coefficient is best when there is some linear relations between data. If there is this kind of curve linear relation, so this is linear, and but later it is curving, correlation coefficient may not be the best descriptor of this data. The other thing what you may consider using in your analysis is what is called partial correlation. So it doesn't measure correlation between only two variables, but also takes into account third variables. So it measures how correlations between two variables, what is the correlations between two variables, taking into account influence of the third variables. So let me give some example. Let's say here we have three different measurements. So let's say that Z it is value of temperature outside, X it is temperature in one room, Y it is temperature in other rooms. So those are three temperature measurements outside, in one room and other room. And here we can have, let's say, across different days. So on one day it is cold, and let's say this temperature outside is nicely linearly increasing, that here is the warmest day. And similarly, temperature in rooms are increasing. And if we look at correlation between temperature in room 1 and 2, we will find that this is highly correlated. But the question is how this correlation is affected by this external temperature. So if we plot X versus Z, we have also this linear high correlation here similarly. But now, if we would fit some regression line to this data, and now we would rotate this data or subtract from X this predicted values of Z, so this points at regression. So from this X, we will subtract what is this red value at this red curve at given Z. So at Z2, we will look what is the point on this curve and subtract it from this. So here is this X minus Z, and this star means that it is not original Z-scores, it is rather this values of this fitted line. So if we do this for X and Y separately, and now we will plot this Y minus Z, and here Y minus Z separate versus X minus Z, we will find that now this distribution is not linear, but rather it is a cloud of points. So if we look at this correlations between X and Y, it is 0.9, X and Z it is 0.95, similarly high for X and Y and X and Z. But this partial correlation for between X and Y, when we would take into account effect of Z, we will find that this is close to 0. So this is what partial correlation is doing, is calculating what's the relations between X and Y, taking after taking from those two measurements what can be explained by changes in these third variables. So by taking what could be explained by z from x and y, it means that all those changes in rooms and 1 and 2, it were not so much that two rooms are next to each other, but it was directly affected by external temperature, and all the relation here between those x and y could be explained by this third variable z. So partial correlations can be also very useful tool to investigate how the third variable affects correlations between two other variables. The last part of this lecture, it will be about decision errors. So probably most of you heard about type 1 and type 2 errors. Type 1 errors are usually called false positive. Type 2 errors are called false negative. Also, it can be called alpha and beta. So alpha probability of making type 1 error, or beta it is probability of making type 2 error. So how to illustrate it? For example, we have two distributions. Let's say that this is distribution of temperatures of healthy people, and here in green is distribution of temperatures of people with flu. And let's say that based on this simple temperature test, we want to somehow classify those people into healthy and sick people. And the idea is that we want, let's say, those sick people to not mingle with healthy people to prevent this flu from spreading. So because those temperatures overlap, we will never be able to design this classification just based on temperatures to perfectly distinguish between those groups. So for example, if we say that, oh, here is our threshold for classifying people with flu and healthy, then in fact we will classify correctly majority of healthy people, we will classify correctly majority of people with flu, but nevertheless there will be some fractions of people with flu which do not show this high temperature, and they will be incorrectly classified as healthy people, and also there will be quite a large number of healthy people which are classified as having flu. And notice is that there is this mutual relations between type 1 and type 2 error, that if we shift this classification, let's say here, to this optimal point, then optimal point that here will be making the least error when those two curves meet. But so we will reduce this type 1 error, but we will increase this error to type. For example, maybe we want to make, but sometimes it can be useful to increase one error type on the expense of other. Let's say that this flu is really very dangerous, it's very deadly flu, and we really want to make sure that all people with flu are distinguished from healthy people. So probably we want to shift this classification even somehow here, that we will have this all people with flu classified correctly, but by doing this we will increase quite a lot of this type 1 error, that we will classify a lot of these healthy people incorrectly. So if we, for example, have some medication to give to those people, then a lot of healthy people will be unnecessarily medicated if we shift it. Here is another presentation how to think about this error type that you can think as this table, that here it is this correct classifications and correct rejection, you may think, and here it is mistake in classifying something as a correct, something what is incorrect, and here classifying as a incorrect something what is correct. And in this cartoon example, you can think as this correct decisions, so this healthy people, let's say that it was 70 of them, it is correctly classified, but there will be this 30% of 30 people which will be incorrectly classified as non-healthy. And here we will classify 50 people from this group of people with flu as having flu, but there will be this 10 people which based on temperature were misclassified as healthy, which are in fact sick. Okay, so this will conclude part 2 of this basic statistic introduction, and most of the concepts which I was talking during these classes will be followed in MATLAB exercises, which will be in part 3. Thank you.